Hello, everyone. So going back to what we had from last week, uh, we went all the way to define this remove node uh, graph. It removes a singular node from the graph, uh, and it creates a subgraph that has that node removed and all edges associated with that node removed. And the goal that we want to prove, like the very final goal, is this path decidable. So the idea is we want to find a path between A and B, or say that there isn't a path, such a path, and we're going to be looking, like the thing that we have to query with is a path within the removing the A from the graph, or any two nodes A and B. Uh, we last time we created this one lemma over here, uh, remove node path, that tells us that if we have a path in the by removing the particular node n, and we have a path from A to B, then we should be able to recover a path within the whole graph from A to B. So what we that would handle the left side of this. If we have the path from the removed node A, then we can recover the left hand side, that we can recover a path from A to B in the larger graph. But it doesn't handle the other case, the negation. And to prove this negation, we sort of need this lemma, but in the opposite direction. We want to know that we can convert from a path between A and B into a path within the subgraph. But that doesn't work in the general case. Specifically, if this path goes through n, then we fail to recover a path in the removed graph. But a certain subset of these do actually work. So we're going to try to define that subset of the path. But before that, we're going to take a little bit of a detour. We created these lemmas in between here that we said were like pretty obvious about the set library, and we just didn't know how to prove them at the time, or like it would have taken effort. But as it turns out, I found out that there's these at the very top here. When we create the module of our set with this make ordered, and we search here any functions related to x dot exists, we only find this one function. But there's a whole bunch of these library functions that define information about this set S. So it's a whole bunch of facts and properties and even more properties. So after loading all of these in, we do the same search, and we see that there's quite a whole bunch of these. And some of them are like repeats of each other, so I probably don't need to import everything. But it doesn't hurt to have things repeated over and over again. Uh, and this s.exists is going to be the thing that we use to implement our desired lemma. We want to find a particular neighbor of the first node that has a path. So we can travel to the neighbor and then travel down that path. So I do have a general idea of how this is going to work, but I haven't really tested it out yet. So hopefully everything works. We can start with proving the two lemmas that we had neglected to prove, the two small lemmas. Let's see if the new library definition helps us with that. So this one has to do with the subsets and in. So let's search. There's a whole bunch of these, properties about subset. This is difficult to find, so let's search for s.in as well. We tell it to find the things that mention both of these. And I guess this lemma here might actually be the one we want. And these might also be describing that as well. I guess, yeah, we can try doing this, unfolding what this means. So let's unfold proper. And forget the specific thing here. Let me do a quick search. Respect. Yep. So here we have that the subset implies that everything that is in uh, goes to everything that is in. So this impl is actually this direction of it. Yep. So I guess let's do intros S1 and S2. Let's do it before this part here. Intros S1 S2. And now we split. We want to do proof in both directions of this. Intros H. And then that's H prime. And we are converting between this S dot subset when in the proper in H prime. We can directly apply this impl into the statement here. That's unfortunate. Let's do it the slow way. Intros X HX. Now we apply H. No, let's specify an H prime X X EQ REFL S1 S2 H and that works. Okay. Hx, and we're done. That direction. So that was good. The library function gave us exactly what we wanted. But now for this direction, there another library function that can give us this. Let's do intros h first and unfold subset. Okay, so this is exactly what we want already. So intros h or intros x intros hx apply h. So maybe this was true far more directly than we had actually thought. This is definitionally the same as this thing. Maybe that is the case. So let's try it. Little fixivity just here. Oh, yeah, that actually did handle it. We didn't need any complicated statements. That sort of makes me want to go and remove this from where we used it. Intros x. Yeah, guess we don't really need it there at all. Cool. And in here, let's try that. Yep, we didn't actually need this statement. Where else is it used? Oh, I guess just within our to-do list at the bottom. Yeah, so I guess we removed that one. But for this one, maybe this one involves more work. Intros G and let's search s.in. And we'll look for something that has the plus sign in it. Oh, here we go. Let's actually copy this one. Apply stop properties index, and we're done. I guess instead of calling this lemma, we might as well replace it with the built-in lemma definition. So we're not defining a separate lemma. And it wants nodes of G instead of G. Oh, and it's flipped. Yep. So that gets us back to where we were before, but now we cleared off those two admit lemmas that we actually didn't need because they were built into the path definition, like the set library definition. And yeah, so now we want to convert from this path into this path. And we're going to say that we want this lemma here. Lemma path path neighbors. For all G graph and A B node path GAB if and only if s dot exists the within the so the type of exists is this s dot element to bool, so a function, and then s dot t, which is the set of nodes, and then results in a bool. So the set of nodes is nodes of G. So we're going to decide whether for any particular node n, we're gonna check whether so we want this condition to be true only when there is a path, and there is a path between A and B. I guess we also need A is not equal to B. If and only if there is a path from the edges VAB. So there's like a single edge between A and N. And then there is a path from N to from N to B within G. And this does not make type sense because edges here returns a bool. So, and we do want to return a bool, but path here is not a bool. How do we convert that path? Let's try writing the same for all statement within the actual induction proof. Third, I guess we don't need the for alls anymore for this condition. We're going to state that the path between A and B exists only if this is true. And here we do hrem of NB match this with in left, or I think we can do an if then true, false, false. Oh, this is, we want an edge here, so from A and then to N. Okay. So if we can prove this statement here, then we should be able to get this statement out here. So let's admit this first statement and go to the second statement. So we have this H here, we can call it something else. H neighbor. Hopefully I'm spelling neighbor correctly. Hmm. That's weird. I think it just glitched out there. So here, assuming we have the H neighbor, we can rewrite H neighbor. What happens here? There's some weird issues here. I don't really know what this means, but I guess we can destruct this thing. H. And H. So now we destructed true is equal to true. So we do have the path. So we're going to be doing left apply H neighbor auto. And then in this one, we say that if we have a path, then we know that false is equal to true, which is impossible, so we don't have the path. So we're going to go right intros H, and I guess we already have an H, well, H prime. So now we have a path, so we should be able to convert into false is equal to true, which is impossible. Apply H prime or H neighbor in H. Now we have false is equal to true, and discriminate H prime. Cool. So now the only thing that we need to prove is this conversion here. That if we have a path, then it should be the same as finding one neighbor, n, and knowing that there is a path between it. So now let's search for how do we prove this? This statement here, the main idea here would be I guess we can prove the forward direction pretty easily. Let's do that first. So the forward direction, intros P for the path, and we want to prove that there exists one particular node. Oh, I guess I do need that A is not equal to B. So let's first do that. And we have equal decidable for the set S, so s.eqdec destruct s.eqdec AB open H. Oh, that's not the EQ deck that I wanted. I wanted node ordered. Node ordered .eq deck. Yep. So we don't want H actually. We want H or H. AB, AB. So in this first case here, we have that node ordered equal A and B. So can we do substay here? We first need to unfold node ordered.eq in HAB. That gets us A is equal to B, and now we do subs B. So now we just need to prove that there's a path between A and A, which is just obvious because A is in the graph, so it should be a valid path to go from yourself without moving anywhere. So left, and now apply path raffle, and we just need to prove that s dot in the node to G, apply HA, and so that side is done. So now if we unfold the equality here, we have that A is not equal to B, and so this is the more complicated proof here. So we have a path, and we know that A is not equal to B, so this path cannot be the reflexivity. So I believe inversion P, what does that give us? Yeah, so in this first case, it's impossible because it gives us this goal of A equal to B, and we know that A is not equal to B, so by contradiction. That clears out that case. And then in this other case, we have this particular n that, okay, I guess we're starting from A. We're going to be doing a subst n. Subst n. And we have a from E and a to E representing a particular edge E that's in the graph. I'm gonna re-intro. Or like even before the subsession, re-intro. Re-intro. Or not re-intro. Subs as, and here I need to provide the particular names. So I ignore the first case because that's just solved by contradiction. And then the second one we have N E H E H or P prime, and then we'll call this H1 and H2. P E H E P prime, and then only H2 because we got rid of the H1 with the substitution. Yep. Now they have slightly better names. Might as well destruct the E. Should we? Not really. But we should do the subst of the B. Do we want to? Nope. We actually want to do path induction in the other direction, where we're doing from the start of A. So search path. Path edge left. that it's annoying that I sort of built the path by appending stuff to the end instead of the front. Uh, so this is actually like if I just do induction like inversion on this structure, it'll give me a appended to the right version of the path instead of appended to the left version of the path. Uh, so I do want to convert this into I guess we could sort of plug it in here, like into the left version. But that doesn't tell us one needs to exist. Uh, let's do another lemma. Lemma path uh, path left path GAP, but only if exists a n such that the edges G so first thing that we want to prove is there exists a path edges that and path G A G and B. A B is equal to true. Okay. Admitted. Let's see how we can use this path left to rewrite over here. Rewrite path left. Cool. So here we can actually get a lot closer to the final goal that we want. And we can do a little bit stronger here. Let's actually do not this path, but a path that never travels through A ever again. Let's define that. And I'll just copy paste the path from before. So here we are traveling through the graph G, but we need to avoid the particular node A. And we find a path between these two nodes. So reflexivity, n is a node, it's in it, and n is not equal to A, applies path n in. Then we go through the edges. I guess I just realized that we do need to add an extra statement to make this actually true, but we'll get to that later. So yeah, n is not equal to A. And here we need to know that I guess we'll do all the checks. And it's not equal to A. From me is not equal to A. And 2E is not equal to A. From knowing that this path works here, we already know that the N1 is not. We don't need this statement. And we also know that the from me is not. So we just need to also know that the 2E, the thing that we result in afterwards, is not A. So we don't accidentally go back to A. Path not. I'm going to call it path not. Update the word path everywhere. And here, path not, going through, we're ignoring the existence of A. Not, okay, I'm missing the A here, and the A here, and A here. Yep. So now assuming this path left, if we do the rewrite of the path left in here, we are currently very close to this. I do want to add the extra case in here that there isn't that A like the A and N are not the same thing, and I should add that to both statements. So there exists an N such that N is not equal to A, and so assuming A is not equal to B here. Cool. So now we have N is not equal to A, so we are actually traveling through one particular node, and then we have this statement here, path not. Although I guess, yeah, we don't really need it here because to even state that we have a path not, we need to have proven that N is not equal to A. So yeah, I guess it's not needed in here. It is needed down here. Within this statement here. So we also need to check that node order dot eqdec an. So there's 3 statements that we're checking in here. If they're equal, then false. False, true, to be able to state that they are not equivalent to each other. Then we have it isn't actually an edge within the graph from A to N. And we find some subpath between N and B. Yep. The first thing we do is rewrite path left. And then we can clear out this goal over here with an auto. And then we can convert this exists. Search s.exists. See what limits we can get out. And we like this one. Exists B F S element. So let's try that one. Wow. I guess we do need this statement here, but let's try auto for that, because equality happens to be the uh, the built-in notion of equality, the Leibniz equality. So try unfold EQ and then auto. So I guess we need let's just try auto. How do I unfold EQ in there? I unfold the node order dot EQ. Is that the EQ? Let's just zoom into the second goal here. Unfold EQ. EQ is not. It says EQ, but it's not EQ. So unfold proper. Unfold respectful. And I guess over the equality x is equal to y, then we want to state that these two things are equal. This should just be auto. Yes. Let's do intros. Intros x, y. Intros to intros the rest of the stuff. Oh, it's just x equals y. X, y. Then subs to auto. Yep. Okay. That was a slightly more confusing goal to prove than I would have liked, but it is fine. And now we change this into the exist b instead. So search exist b. Not what we want. I guess we don't want any of the ones related to S. We just want the ones within the list library. So this exist b exists. It's equal to true means that there exists something in it. And, so let's rewrite by that. So we started with this exist b, and after doing the rewrite, we have this exists like this. And now we're getting pretty close. We want to prove that this node is actually the same as this node and vice versa from each other. So yeah, let's do that. Let's do a split. Clean up a little bit here. So a split here. And in the first branch, intros n h edge and p for the path knot. So we introduce these three things. And now we state that the same n, so exists n, is the one that solved this thing. We want to know that n is in the nodes of G. So we want to derive that path knot implies that in n of G. Then that path knot in G, A, and B. So we want to know that path knot G A N B implies that the uh in S dot in nodes G N and S dot in B nodes. So as a proof, let's actually convert these into overall. For the sake of consistency. And we have something very similar to this proven before. Let's see if we can just copy paste it. Path in graph corresponds to, for the path version, we have the ins. Going back to the not path, the path not version. I guess we need an extra n in here. And h naught, h naught. Now they are properly named. So this first one should be exactly the same as before. And hopefully this one, does this work? Yep, it actually does work. So QED. That was pretty easy. Then the lemma that we were proving inside of here, we want to prove this side here, so let's do a split here. Search s dot in with in and s dot elements. Remove in. So it is this one here. Flipped. So apply this. Nope, did I get it wrong? Let's search it again. So we want an in and elements. Search in A. I think we proved the lemma about this. Yep. Apply this. Then let's do the same search as before. And this one. Apply this. And then we want apply path not in. Let's fill in a few arguments into this. I think that's how many arguments we need. Yep. That helped the unification procedure figure out what the type of that was. Now we just need to prove the remainder of this. So let's actually destruct this thing. and we get this term in here as h or h. In the first case, we know that we want to show that path naught implies that a is not equal to n, because we couldn't have gotten a path between there. So for this case here, bold node order q of h. Let's call this an. Now we want to show that path naught implies that a is not equal to n. Copy this introduction here, and we'll state that if we have a path naught, then n is not equal to a, and b is not equal to a. Path not equal. And see what happens if we just try this. And we actually have everything that we need with split and auto here. Even simpler than the lemma before. Path not equal. So apply path not equal in HAN. Path not equal, we need to put the underscores and then P. Oh, it is flipped. That is unfortunate. So destruct as H prime. We only really care about the first half of it. So we have a is equal to n, and n is not equal to a. So contradiction. I guess I couldn't actually find the contradiction. We need to manually switch this to subs a. So now we have n is not equal to n. Now we can do contradiction. Cool. Then yeah, so we are left with that a is not equal to n. A is not equal to n. And we have true and, so we can just simplify a little bit. And the true and gets reduced to just the right-hand side of the and. So now we do have this thing in here that the edges is equal to true. Let's just do a rewrite h edge. Now that is just true, so we can do another simple. And we have left with this particular case. Destruct h rem and b as p prime h p prime. So now in this thing here, we just have the path is equal to true, like true is equal to true, so it's auto. But in here we have false is equal to true, so that's impossible, it's falso. Now it's just saying false, and we can apply HP prime and clear HP prime. So we need to go from a path not into a path that is removed. And that should be possible because path not ensures that we don't actually travel through A. And this path means that we don't actually travel through A. So they actually do work. So there should be a lemma for this. Let's actually write out that lemma. Path not convert the path not remove node. Let's do it above the path left. Path not remove node. So if we have this path, then we should have this path. Let's make sure that this makes sense. This implies that A is not equal to N, and this side does not imply that A is not equal to N. So we need to add in the thing in here. I guess we just need, let's just add these two assumptions here. So A is not equal to N and A is not equal to B. Then these two things are equivalent. This is for all G, A, B, and committed. And we can use this right away down here. Apply path not remove node, and then just auto. Ooh, and that clears off that goal. We still need to prove that gigantic lemma of path not. But let's focus on the other direction of this. This should also be pretty straightforward. We introduce a whole bunch of stuff into the context. Intros, N, and then HN, and I'll call this gigantic thing H. Oh, I guess I'll need to be missing those braces. Yep. So we have N, we have that it's in the nodes, and we have this statement here. Let's convert the in the nodes over to the other thing using these things. In HN, HN. Right, 2 there. Yep. So now we just have the s dot in nodes of G instead of it's in the elements, making it cleaner. Then we have this gigantic blob, and we know that this blob is equal to true, so we're going to piece it apart piece by piece. So let's destruct this thing and try contradiction, or try discriminate H. HAN, HAN. I'm going to do it without the try discriminate first and show you what that means. So first, the H is equal to, it's just false is equal to true, which is impossible. So the try discriminate H will clear out that particular thing. So if we try the discriminate H, we just get rid of the one branch and we just are left with the true version. So simple in H. Now we do the same with this. Destruct when H edge. Try discriminate H. So we once again have this new statement here, h edge, and we are left with the h true there, so simple in h. And we have this final one here, construct hrem as p hp terminate in h. So now we have just left with h is true is equal to true, so we can just clear h. We don't need h anymore. But we have a path from remove node A, G, and B, and we want to prove this gigantic thing. But we should also unfold node ordered eq in HAN to clear that up. A is not equal to n, and A is not equal to B. So now we plug in the n exists n, and we have this statement here. This left one we already have with the h edges, so split auto. And we just need to prove path not, and we have the path remove. So apply path not, remove node, auto. Cool. And we are done with that. We can actually close off this thing, UED. Oh, I guess I changed the definition here slightly. Let's copy paste this thing here actually. Yep. So now this matches up to the thing that we are destructing. In the left case, we are done. In the right case, we are done. So instead of UED, I'm going to call it. Yep. So now we actually finished our gigantic lemma, the path decidable, but we have these two admitted. Let's see, admitted. We have just these two admitteds left. And they are pretty big admitteds, actually. But I think we can tackle this first one. Intros GAEN. HAN, HAB. And for here, we're probably going to, I guess we need to do split and prove both directions separately. In this direction, we have a path not. We want to recover a path with the remove node. So intros P, and we want to do induction on the P. Grab this induction thing. In the first case, we want to prove a path within the remove node AN. So that would just be apply path refl, and we just need to prove that it's in the nodes of remove node n. If we do a simple, we just need to show that s.in, s.remove, search s.in, s.remove, see what that gives us. I guess we can do this one. It's called remove 2. Another remove 2. So remove 3. There's also a remove 1. We do want remove 2. So apply remove 2. This is the cleanest one. No, this one is the, we want the s.facts one. Apply s.facts remove 2. So we want to prove that something is in the remove version. So that means that we just need to prove that n is not a, and n is in this thing. So we need to prove that a is not n, and n is in this thing. Try an auto. Oops, I pressed the wrong button. Yep, and auto just cleared up both of those goals. That was pretty nice. And now we have our IH, this complicated statement here. And we want to prove that there is a path So we do apply path edge. So we want to prove that edges of the remove node E is true. And for that, we basically need to know that it's within. Let's just do this simple. We do a simple instruction, simple. Then it expands it out into this thing here. We just need to know that the from E is not A and the to E is not A. Then we just get the edges E true, which is that part over there. We can even rewrite it. And then in this part here, this corresponds to the IH. So we can just apply IH. Let's try auto actually. Nope, it didn't actually solve it. So let's do them step by step. We'll start with the first one. We can do a rewrite of the H naught. I guess it is not H naught. HE, H naught. There we go. I had to flip those two terms. Rewrite HE. Then we just need to prove that this thing and this thing return true. So let's just destruct them. Destruct. As h1, h1. So in this first case, we have false is equal to true, so we want to reach a contradiction. So let's unfold this thing in here. Unfold node ordered.eq in h1. And we want to know that from E is equal to A is false. And we get that from the path not here. So if we apply in E, we see that we don't have this from. So destruct E as 1H2. Let's actually do these two steps earlier. We'll call this H3 instead. And here we can just do a subst contradiction. Yep. Quite a lot of spaces after that. And then continuing on, I really won't actually use the braces because it makes more sense to say that we're continuing on after having proven the smaller case. We don't even need to keep H3. I won't unfold it there. I'm just going to do copy paste this thing, H4, H4, and this is the 2E, and then H4 subs contradiction. And then this last one was just true is equal to true, so reflexivity. Cool. Now in here, we want to use the IH. Apply IH. And we need to know that A is not equal to N, which is one of our assumptions here. And A is not equal to from E, which we can get from this statement here. Let's do an auto. And then let's copy these lines here. And do another auto. And we're done. With that particular, we finished that direction. And now we need to prove the other direction. So, intros induction H, or intros P, induction P. The induction is going to match this thing, but we remove the H naught. So we have that it's in here. So let's just expand it out. Simple nh. We know that it's in the s dot remove. I think it's we changed this. Let's just try the number of 1 in h. What happens there? It's not exactly what we want. We might want the version 3. Yep. That converts us into there. We know that it's in the nodes of G. And we know that it's not A. So we can do apply path not refl. And this pops out these two goals, which are stuff that we have in the context. So this is just auto. Yep. And then for the induction case, this one is probably a lot more interesting. Is it? No, it's still pretty straightforward. So we do an apply path not edge auto. We don't need the auto. Oh yeah, we do need the auto. The auto managed to clear that part. And we now have these two statements here. We can convert the HE simple in star. So this part here we can destruct. Destruct as h1, h1. And in here we have false is equal to true, so we'll do a try discriminate he. Let's actually do this before we do the apply. So first step here, we do a simple everywhere. Then we destruct the node ordered EQ. And we clear off the thing that doesn't make sense. Then unfold in h1. And let's copy these two lines and we'll change it to the 2e, h2, h2, h2. And so we have left this thing here, and we have a whole bunch of these. Maybe some of them are repeats from each other. Not sure. I don't care to look. Oh yeah, this one is a repeat of this one. We didn't actually need it. Then if we apply path edge and auto, then we are actually done with everything that we need. So that is a QED. And we have proven path not remove node. So the only thing stopping us from our huge lemma is this small thing that we have left here. We're actually getting pretty close. I can still go for a little bit more. Let's try to prove this and see where we get stuck. Intros G, A, B, H, A, B. And here we have a actual path, and we want to convert it into going down a particular neighbor and finding a path not of that neighbor. So I'm pretty sure the right to left version is pretty easy here. It's going to look very similar to our previous lemma that he did here of the remove node path, because this is like roughly equivalent to the remove node path. Actually, we could even do that. Yeah, we can actually just use this lemma. Let's even do that. So split, and we're going to start with the second direction. And intros, N, HE, and a P. So we have a path not, and we know from a path not we can convert it into a path remove. And we have this A is not equal to B, but we need to deduce the A is not equal to N. So let's do an auto here. Let's solve the second case first. I guess we should, let's first do the A is not equal to N as an assumption. Or let's just do the destruct. We have path not equal to, so destruct 1, 2, 3, 4 P as H1, H2. And now we can do this thing and auto. And we have left to prove that we have a path in the smaller graph, so we have a path in the bigger one. And that's the lemma we proved last time. Remove node path. Do an eApply. eApply, remove node path, eAuto. Guess I couldn't figure it out. Let's just give it G A. Oh, we're actually missing the apply path edge. eApply path edge. So path left. Path edge left. Yeah, it's path edge left. And then eAuto. And now we have left to prove that path is there, so we apply remove node path eAuto. We're done. Cool. So we just used the remove node path lemma from before. We could have proved it again, but we had that to do a bit of conversions and get that out. We just need to prove this direction here. And this direction is pretty interesting because this path here, we could have potentially revisited A in that path, but that means that we went through another smaller path to go from A to B. So we can still do that smaller path is still known to do this conversion. So doing induction on this bigger path, we would still be able to get out the let me try explaining this in a diagram. So like, let's say that we go A to B, but we go through C, D, E, A, F, G, B. So here we have a path from A to B, but it repeats by going to A. So we don't really have a path not. And as we're doing induction, we end up finding that like, okay, we have a path up to this point for the A, and then, oh, we revisited A. And if we revisited A, then we know that we have a smaller path from A to B, which is this path here. So we don't actually need the bigger path. We just could have gone through the smaller path. And that's the dilemma that we want to be able to state here. We can convert this path A to B into a path that doesn't travel through A ever again. Intros P. Induction P. That's this statement here. And for this first case, we have n is not equal to n, which is impossible. So try contradiction. That clears out the first case. We have left with the second case. As long as n is not equal to from E, we have the IH. But in the event that it is the n is equal to from E, we should be able to automatically get it. Okay, so we're traveling from n, starting point n, and we're going through the to E to the from E. wait, we want to build the path not through induction but in the other direction. Yeah. I will I'll spend some more time thinking about this lemma, and I think we can stop it for now at this point. And I'll see you guys next week, and hopefully I have a better solution to this lemma. Uh, just to recap before we go, we went ahead and wanted to prove this path decidable. And so when we got down to in here, we wanted to convert from the path of the removed node, the removed nodes, into the path of the larger version by first traveling down one particular edge and then continuing on to the remainder of the path. So we can describe that process here with this statement. So this is saying that there exists a path between A and B, but whenever there exists a particular node in the nodes such that that node is not A, and there is a edge between A and N, and if we remove, like if we follow a path between these, like the N and the B, then we can recover the path from A to B by just traveling down this edge and then going through the rest of the graph with the removed A. So that is the and within this statement here, this was an easy conversion using all the built-in tools inside of the set library, like the s.facts. We scroll down, we end up proving this whole thing. It takes a while. And then once we have proven it, we can just, this is a Boolean, so we can case analyze on whether it's true or false. So if we destruct it, we know that in this case we do have a path because it's true. And in this case we don't have a path because it's false. So that's how we define this particular lemma. So in doing so, we pretty much indirectly added in an algorithm into here. We're embedding an algorithm within the proof, and we're using that to determine the proof. We'll see this chunk here will appear later on again. Yep. And to finalize that proof, the only thing that we have left to prove is this statement here, which is that we can construct a path between A and B that doesn't go through A more than once, which is the statement down here. Thanks for watching, and see you guys next week.